All right. Hello, y'all, and welcome to our last workshop on binary exploitation 2, because one binary exploitation was not enough. Yes. Okay, so first, a couple of announcements. This is going to be the last workshop for the quarter and the school year. But don't be afraid, because we still have one last event, which is CTF After Dark in 2 weeks. That's going to be on Wednesday, same location. It's going to be the kickoff for CTF After Dark. It's going to run for Engineering 6. So if you're free, please come and voice your opinions about the CS department. You can complain about the classes you don't like, stuff like that. Yeah, that's
We also have Cyber Social Week 9.
Oh yes, we also have a Cyber Social Week 9 after all of our academic events, just to chill and hang out. Probably going to Sawtell for that. Yeah. Okay, so this is our agenda for this meeting. We're going to start off with a review on stack and buffer overflow from last week, and then talk about ROP, which is the second half of the attack lab. It's very important. And then we'll go on to talk about code injections, post-exploit buffer overflow, and then some virus stuff at the very end. And this is a very accurate graphic of how you inject binary into your laptop. So a quick review on the stack. On the left picture, you can see basically the big memory layout of your computer's memory. At the bottom is the low memory address. At the top is high memory address. So you can see stack starts out at high memory address, and then it goes down. However, when you index an array or something, it goes up on the memory address. So this is why we can exploit that for stack overflow. So on the right, this is a zoomed in picture of just the stack. The same thing at the bottom is low address, at the top is high address. You can see when you call a function, it's going to save the return address here, and then it'll use the stack somehow, and then maybe this is in an array or something. You can access it, pass the array, hit the return address, and then go on to other important information. You can overwrite that if you have a buffer overflow. Yeah. Also, feel free to stop me at any time if there's any questions. Yeah. So for buffer overflow, when we overflow the buffer, this is basically saying we allocate, let's say we allocate 32 bytes for the input, and then we read in the input, but we read in up, and then we overwrite the RBP, and then we overwrite the return address. So instead of returning, instead of returning back to the original function, we can return to anywhere in the code. And then one other thing is that you can even write arbitrary code beyond the return address. So let's say you write some assembly code over here beyond the return address, and then you set the return address to be that location. Then you can run any code you want with the buffer overflow. And this is basically what you're going to do for the first half of attack lab. Writing code and then writing arbitrary code and then changing the return address to that is because now computers are more advanced. Some sections of memory are marked as executable. The other parts are not. So for example, the stack is usually not marked as executable because you usually don't have code on the stack. You usually have code in a separate section. So if you were to have code there and then you change the return address, the computer will tell you, hey, you can't return to that because that's not valid code. That's not a function. That's probably data on the stack. So this is good for security, but unfortunately, it's bad for hackers. However, because hackers are smart, they found ways to get around that and still execute some code that they want. So I'm going to go a little bit more into detail about ROP. So instead of writing our own code on the stack, we can basically just use what's already there. So every single function ends with a return, and the return basically just pops the stack, looks at the address, and then goes to that address for the instruction pointer. So let's say you have 3 functions, main, func1, and input. main calls func1, and then func1 calls input. And then maybe you input something. After you input and then hit enter, it'll go back to func1. It'll return to func1. And then after you hit the end of func1, it'll return back to main. This is like the normal flow if nothing bad happens. However, if you input something that causes a buffer overflow and then you return to somewhere else, you can, let's say, have the input return to func2, a completely different function, and then have func2 return back to main. So func2 can be any function that is already in the code. And you don't even have to start at the beginning of func2. Let's say you want to start at the middle of func2 plus, like, let's say, 80 in hex bytes. You can still do that as long as at the very end there's a return statement, and that return will just take you back to main. Okay, so how do we get the code we want? We basically use really short segments of code called gadgets. And then you can chain together multiple of these short gadgets to get the result we want. So for example, let's say you want code that moves the value in RDX to RAX. Maybe you don't have that code within the function, like there's no function that just does that, or not even like the very bottom of the function does that. You can split it into two gadgets. So maybe there's a gadget that moves RDX to RBX and then returns. And then there's another one that moves RBX to RAX and then returns. So if you chain these two together, these two just have the effect of moving RDX to RAX. So ROP is more effective when code is long, because if there's like a lot of functions in that one file, it's really easy to find code that you want, and that's usually known as like a gadget farm. There will definitely be a gadget farm in the attack lab. So you just need to parse through like all the gadgets and then see which ones you have and how you can use the ones you have to get the result you want. So these are some common gadgets. So this is just a lot of info, but just know that every single one of them needs to end in a C3. So let's say you want like pop RAX or something, pop Q RAX. You can see in part B, encodings of pop Q instructions, and then the first one is pop RAX. So if you see like the bytes 58 and then C3 in the code somewhere, you can set your return address, like when you buffer overflow, set the return address to be the address of those bytes. And then like once it executes that, it will just pop RAX off of the stack and then return. So then you can basically control what RAX is if you input something onto the stack. Some specific input, you can like somehow chain together gadgets that pop RDI. If you can do that, then you can input whatever you want into the first parameter of a function. So this might seem a little too good to be true. What if there's not enough function calls? So let's say like before we had main call func1, call input. But what if like main just calls the input? Like what if there's no like return values and stuff? So the thing about that is the stack contains both return addresses and data, and it's all like mixed together. It's not like all return addresses together and then all data together. So you might be overwriting return addresses and data at the same time. And then at the very end, maybe you have to return to like this address, but that address is actually data. And then the program will scream at you and say like, that address doesn't exist, segfault. But the thing is, the program still runs up until that point. So it doesn't matter, like the program didn't end with like a exit code of 0. You can still get the information you want and then have the program die. So here's a pictorial example. This graphic is nice in the fact that there's like functions, but also bad in the fact that they flip like low and high memory addresses. So on the very, very left, that is an upside down picture of how like memory is usually represented with low addresses at the bottom and high addresses at the top. So you can think of the stack as going downwards. So each of those corresponds to like one on the right, but they like flipped it. So if we were to like have The first one, the yellow one, the thing that ends in DE, be the first one. You can see that like DE, if you follow the orange arrow, that has a code of pop rex and then return. And then when you pop rex, it basically looks at the stack. The stack is now pointing to like the red thing. And now rex will equal that. And then once it returns, it'll pop to the purple thing. And the purple thing is like move rex to rdx and stuff like that. So you can see like if you input a bunch of, a mixture of data and return addresses, you can achieve like a pretty solid string of code that like does complicated things. Yeah. Okay, so I talked a lot about what we can do with ROP, but there are some limitations that you should know about. The first one is ASLR, which is something that's implemented nowadays a lot. So ROP isn't as common. And ASLR stands for Address Space Layout Randomization. So ROP only works if you know where every gadget is and the address of that gadget doesn't change. Because now there's like ASLR, they like mix around the locations of the functions. It doesn't matter to the compiler because like if you know where the function is, it's fine. It doesn't matter if this function is first, this function is second. But that just prevents the ROP attack from happening. The next thing is gfree. Gfree prevents misaligned return calls, which basically means that you can't like you can't go to an address that's like in the middle of a function. You might need to start at the beginning of a function or like in 8-byte chunks or something. So you can't just do the 1 byte of like pop rex and then return. So that limits the number of functions that you can do with ROP, which is why that is also bad. And then the main part of that, of ROP, is that you first need a buffer overflow vulnerability. If they don't have a buffer overflow vulnerability, if they don't use a function like puts or gets or scanf, like one of those vulnerable functions, then you can't do ROP. That's like the entire basis of ROP, returning to something that's already in the code. And then the last thing is that you need code to already be there. So if the code is extremely short, like if it's just like a main function that does exactly what it says and there's no like random code elsewhere, it's really hard to find the gadgets that you want. Yeah, so you basically need the person coding this to make a lot of errors. So now I will do a quick demo. Let's see, where's the terminal? Okay, cool. Okay, so here I have, wait, can everyone see that at first? Do you need me to like zoom in or stuff? Is that good? Make it bigger? Okay. I'll make this full screen. Cool, thank you. Okay, so here I have a couple of files. So the first one we'll look at is demo1.c. So this file is basically exactly the same as Benson's demo from last week. You basically enter some text, and then like it returns what you entered, and then there's like a secret function elsewhere. So you can, I've compiled it already with demo 1. So if you do demo 1, you can enter whatever text you want, and then it returns what you entered. So the way you call the secret function is basically you first have to see where the function is. So object dump demo 1, and then you get a lot of code. You can see that the secret function is at location 4005C2. That would be very important. And then the other thing is that in the echo function, right before calling scanf, it decreases 20 or 20 in hex bytes from RBP. This is like the buffer. So 20 is equivalent to 32, and then there's also like 8 extra bytes for like the return location. and stuff. So basically, we need to overflow 40 bytes to get to the return address.
So by 40, 24.
So 20 is, or like 20 in hex is 32. So 32 bytes is like the space that's allocated. And then there's another 8 bytes for like the RBP, I think. So like because this is like a 64-bit machine. So like 64 bits is 8 bytes. So there's that extra 8 bytes for the RBP that we also need to overwrite. So this is like exactly the same as Benson's demo. I'm just like doing it again to refresh. So what we can do is we can run Python directly. So Python-C runs Python directly in the terminal. So we want to print, like, let's say the character A 40 times. And then after we overflow the buffer, so this A just takes up the 40 bytes, we want to have the location of that secret function. So that secret function was 4005C2. So 4005C2. And the thing about this machine is that it is little endian, so we have to like swap the order of that. So instead of 4005C2, we have like C2. Do like the \x for each byte. So \x, and then this would be like that location. And then there's also a couple of zeros at the end. This is only 3 bytes. Each address is 8 bytes long, so we also have to pad it with like zeros at the end. This is not really this is at the end of this, but it's more of, think of it as like the beginning of the address. The address starts off with a bunch of zeros and then 4005C2. So yeah. So if we just run this, you can see that it prints out a bunch of A's and then some characters that we can't see. But if we pipe this into demo 1, hopefully this works. So you can see that you enter the secret function and there's a segfault. So the segfault was what I was talking about, like, it doesn't end with nicely with like an exit code of 0, whatever. It's going to return, it's going to go to the secret function, finish the function, return, and then realize like once you return, it returns to some data, some garbage address. Yeah. So that's basically like a refresher of that. We're going to use the same idea to implement ROP. So demo2.c is the other one. So the main function is the same, the echo function is the same, but now the secret function has this extra step that it takes in a parameter in A, and it checks if A is equal to 1. If A is equal to 1, you get congrats. Otherwise, you don't get congrats. So doing the same thing, you can do object dump -d of demo2. So this is slightly longer. The secret function here is at 4005EC. So if you do the exact same thing as before, so 4005EC, and then put that into demo2, you're going to get, like, you still run the function, but it's going to say A is not 1, A is actually 0. So somehow you need to change that first parameter to be 1. So if you check these slides, can I go back to the slides really quick? Thank you. So the common gadgets, I don't know if you guys can see that really well, but the first parameter is RDI, and we want something that changes RDI. So one thing that can change RDI is the popq instruction, popq RDI, which is 5F. I know this code, and I know this code contains 5F, but sometimes you need to like search for it, like look through the assembly and see if any of it matches. So we're going to be on the lookout for 5F and then C3, because C3 is a return. I think you can go back to that. Thank you. So then if we see here, there's like a couple of like random functions that seem to do nothing, like a set val1 and a set val2. So one thing that I can see is over here, there's like an 5F C3 right there. There's like, this is kind of luck based. Like you just have to see if there happens to be like the gadget that you want. Sometimes the gadget you want isn't there, so you have to use like other gadgets to replace that gadget, stuff like that. One thing that I recommend for the attack lab is maybe like copy and pasting all the gadgets in the gadget farm, and then like Command F or Control F C3 to see like where the returns are, and then see like right before the returns which ones are valid. So here we have 5FC3, and the location of that, this is 4005 E3. The E3 is like the C7 byte. So this is E4, E5, E6, and then E7. So we really want 4005 E7. So we go back down, 4005 E7. And then after this, it's gonna pop the stack. So we're gonna add like a 1 to the stack, so that's like the variable that it pops from it. So a 1 would be x01, and then followed by like 7 zeros, because each register is 8 bytes, so we need everything to be 8 bytes. So we add another x00 times 7. And then after we pop that, we still want to run that function. So that function 4005 EC. So 4005 EC, so that's EC 0540. So, oh, thank you for that. EC. Okay, and then we also want to finish that with 5 zeros, because we want everything to be like 8-byte chunks. This is only 3 bytes. So theoretically, this should work. Fingers crossed. It does not work. I probably made another typo. Yes, this one should have a times 5. Yeah. Okay, so now we get congrats A is 1, so we have ran the function with A being 1. Okay, that was kind of a lot. Does anyone have any questions about that entire process?
You move something into REI, is that what you did?
Yeah, basically. So I have like this chunk of code, so this is the location of the gadget that pops RDI. So this, like the function at this location just pops RDI and then returns. So when it pops RDI, it looks at the stack, and then it takes like the top value from the stack and then puts it into RDI.
Oh.
So this is the top value on the stack, which is like a sequence of zeros with a 1 at the very end. Yeah, so now RDI is 1, and then it returns, so it goes to the next one. So this one is going to be the function that we want, the secret function.
It's running that first because it's a little idea.
It runs that first and then that, because that's like, if you think of the stack, it's going downwards, right? So when we go up, it runs this first and then this as it like returns.
Okay.
Little endian just swaps the order of these. So instead of like having a bunch of zeros and then 4005 EC, you put EC 0540. Yeah. Any other questions? That was a good question. Yeah.
So that means for the first run through, well, basically what made demo 1 work, it was coincidental that the last 4 bytes of the return address was actually 0. Up top, you didn't have the times 5 for the 4005 EC.
Oh, for this one?
Yeah, was there
Yeah. That basically means that like, we started off with like the stack is like memory. Even if the stack isn't there, there's still memory there, so there's still bytes there. So maybe at the beginning, the bytes were all initialized to 0, and we just didn't override it with anything.
Okay.
Yeah. Yeah. So that was also a little bit of luck there. Yeah. So I think you can go back to the slide.
Oh yeah.
Thank you. Yeah, so this is like a color-coded, this is like the last instruction that we ran like the 40-byte buffer is the 8 times 40, and then the gadget out there at like 0x40, 05E7 is that yellow part. And then the 8 bytes for RDI is this, the 0, 1, and then a bunch of zeros. So now this is an RDI. And then that last thing is the return address. And then we type all of that into demo 2 as the input.
Okay, cool. Okay, so I'm going to talk about like sort of the next step in buffer overflows. So last week we talked about sort of calling functions using like by overriding the return pointer, but in this case we're not actually going to do that. We're going to actually run arbitrary code using shellcode. So in order to do this, I'm going to kind of like draw an example of the like attack that we're going to use, and then I'll actually show the attack like on as a demo. So I just want to make sure that you guys can see the board. Okay, so okay, so if we like look at the stack, right? If we think of the stack, you can just think of it as a box where you sort of have high memory and low memory. And we know that RSP is going to point to the bottom of the stack. And at any given point...
Sorry, could you switch the views?
Oh, yeah, sorry. Okay, so...
I think you meant like your camera.
Yeah, you
I see.
Just your name.
I think just go.
You just click it, right?
Okay. Wait,
I'm double clicking.
Technical difficulties of CO.
Oh, wait.
Okay.
Wait, there we go. Oh, wait. Oh, got it. All right, sorry. Okay, so like you can see RSP points to the bottom, right? And this is just the stack frame at any given moment. So like let's say we're within a function at this point in time. So the top of the stack is going to hold the return address from this function. So this is going to be one after the like call instruction. So this is the return address. Okay, and then I mean RBP is sort of like an optional thing, but RBP, if it was a thing here, we would know RBP just points to like here. Okay, so essentially what we're doing when we use a buffer overflow is there will be some sort of employee using getS that has an unchecked length, and it'll just fill up this buffer, which is the stack, and then our goal is just overwrite enough memory that we can overwrite the return address and change where we want to go, right? So now this works great because we can overwrite this return address and we can go essentially to any function within our code. But what if we want to run things that aren't already in our code or aren't already in the binary that we might be given? Well, in that case, we're going to need to use some sort of code that we give the program. And a good place to store that code, which is known as shellcode, will be actually in the buffer. So the idea here is essentially that we'll have some sort of, when we input this, we'll input some sort of code, and then we'll implement a ton of padding, which can be basically anything like A's or things like that. And we can just do this all the way up here until we overwrite the return address. And then in this case, what will happen is instead of overwriting the return address to go to some point somewhere else in memory, we're actually just going to overwrite it so that it points right back here. And then in this case, now what will happen is when the stack gets popped, the return address will point back to the code, and then the code will get run. And this code can do basically whatever we want. So there is one catch though, because I know you guys probably have heard of ASLR, which is just basically address space layout randomization, which is sort of a lot of the time, or at least with the stack, it just sort of, this whole thing is just going to be shifted a little bit in every single case. So we won't know exactly the location of this code because it'll change from time to time. So in order to get around this, we use something called NOP slides. So we'll have basically a bunch of NOPs. And these are just instructions that basically do nothing. So if we do this, what we'll do is we'll basically have this return address, instead of pointing to the code, we'll have it point to, and this is good because it means if this is randomized, we have a much larger like target area for where we might hit. And if we hit anywhere on this NOP slide, since the code gets executed like this, it will eventually hit our code. So in practice, you're going to want to make this really large so that you have the highest chance of actually running your exploit. But in our case, for this demo, it's going to be, well, I'm going to use about 20 or 40. So this is sort of like the idea and like the theory for how we'll run our like buffer overflow exploit. And this code, in our case, for my example, is going to actually run a shell. So essentially, this code will just be some sort of assembly code that, in our case, will just call, or it will just run a program /bin/bash. So that's enough for theory. I'm going to go and I'm going to do an example. Okay, is that too small? Okay, so here is an example. Basically, oh, sorry. So let's say we're given a file, an executable called demo, right? And if you want to look at the source code for demo.c, here it is. And essentially all it does is it'll just run a function, and this function just defines some buffer, and it uses the vulnerable function getS to get some input and put it into buffer. And then it'll just print out like welcome and then whatever you entered. So if we actually run this file, you can see I can enter something like there, and it says welcome word. Okay, so we know this function is vulnerable because it uses getS. But the question is, how can we actually exploit this this vulnerability? So in our case, I kind of talked about it. We need a way to get this shell code. We need a certain amount of padding. We need the return address, and we need our NOP slide. So in order to do this, you could use Python, or you could enter it by hand, but that's kind of a lot of work because this is kind of a mess with so much going on. So I actually just wrote a Python script to do it for us. And essentially, you can ignore all of the comments and things, and you can also ignore this line. But essentially, it'll define some shellcode, and you can get there's lots of places online where you can get shellcode. I linked one in the slides, which I'll go to after. But essentially, if you actually were to decompile or like disassemble this, you would see that it is, sorry. You can see that, sorry, it's kind of hard to see, but basically it's just some assembly code, and you don't fully have to understand what it does, but essentially it just runs bin bash. And what we did was we just took this hex and we put it into our like exploit file. So that's what this is. So basically what will happen here is we need to have some sort of NOP sled, which I just gave it 20, and 0x90 is the code for a NOP. We need some sort of padding, which will basically get us from where our shellcode was in the buffer to the return address. Well, we need to know the exploit location, and in this case, that's just going to be wherever it's pointing to. And then basically what will happen is we'll take our NOP sled, add it to our shellcode, so NOP sled, shellcode, padding, and then exploit location, which will overwrite this. And we know that our buffer and our stack, which we can examine using GDB, is going to be, we have to overwrite 112 bytes. That's from here to here, which I'll show you in a sec with GDB. But we know that basically the amount of padding we need is 112, which is this whole thing, minus 20 for the NOP slide, and then minus the length of the shellcode, and then the rest of this needs to just be A's. And that's what \x41 is. This could be literally anything. It's just there to get us to the end. And then we just add the exploit location, which will overwrite the return address. And then if you're wondering what this is, it basically just makes it so that we can write out what we wrote to, like in a binary format, so that it doesn't get, it's not like you're going to pass in \x68 and then it's going to be like, oh, well, the ASCII for / is this, and we don't want that. We want it to actually pass in 68 as binary. So if I run this, it will generate a file called payload.txt. And here, so we can see that we have a bunch of NOPs, then we have some shellcode, and then we have a bunch of A's, and then we have a return address. So how can we actually run this, right? Well, I'm going to show you in GDB so you can see kind of exactly what's going on. But So let's set a breakpoint. We saw the source code had a function called function. We're going to go to assembly, and then we're going to run with our payload. Okay, so this takes us to func, which is the beginning of our function. And basically, if we don't really care about what's going on here, so we're just going to skip over most of it. But at some point, this will be the instruction that prints out what we passed into it. And this is the thing that was passed in using payload from like standard in. So I'm just going to there's a small bug with GDB that like overwrites stuff, but basically. Now, if we go to this instruction, which is right before the end of the stack frame, we can actually just examine the stack. So 128XB, ESP, and I didn't really explain this, but I had to compile this for 32-bit, which I can explain after. But if we look at the stack, we can see that there's a bunch of 0x90s here, which is our NOP slide, and then after that, you can see that there's some shellcode here, or all these instructions are shellcode. And if we go far enough, you can see that now there's a bunch of 41s, and these are all of the A's. This is all the padding. And then if you go far enough, after all of the padding, you can see our return address, which is FFFFD7A0, because 32-bit. And then if I was to print out the stack again, so it said A0, right? Yeah. So A0, you can see that points right to the middle of our NOP slide. So basically, once we step into this return call, it should take us to our shellcode. So if I go to the next instruction, or the next one and step in, you can see it takes us to assembly that was never in our program to begin with. This is what we actually inputted into our program when I did the the left angle bracket payload.txt. So we can actually just run this now. And then this int 0x80 is actually the system call that starts the shell. So if I do this, it's going to tell me that the program exited, and that's because with GDB, it actually starts the process in a completely different way than usual. So we actually can see that it's running now. If we look at, we can see that it started up user/bin/bash. So in order to enter this, I'm going to have to do it again. So payload. This should take me, if I run it with no breakpoints this time, let me just quit and do this again. Okay, I'm gonna do it. Okay, so you can see it ran here. So I'm gonna run it one more time just for it to be sure. And then if we can actually now see if I run it one more time, then, okay, interesting. Oh yeah, sorry, I forgot. Okay, luckily, if we can't actually enter this program right now because it's technically not, it's not like we don't have a flag set in GDB that lets us enter it. So I'm gonna set that right now. The flag is actually called set follow fork mode, and then basically you're just gonna set it to child. So okay, now if we run it again, you can see inferior 2. So it actually started up a new process. So you can see now there's 2 of them running. So if I actually run, now, this should actually start up the next process. And as you see, you can see we have GDB here, and it has opened up a shell within GDB. So that's sort of the idea. This is sort of like a real-world example of what you can do with a buffer overflow exploit. Like in this case, it's not really, we already had a shell to begin with, but if you were to maybe interact with a program that had a buffer overflow and it was not, like you didn't have access to the shell, you might actually be able to open up a shell using this buffer overflow exploit. So this is sort of just a real world example of what you might actually be able to do with a buffer overflow, and a reason why it can be actually very dangerous, because you can imagine if this was a root shell, you could potentially log in and just delete everything on the system. You could have full access to control the system. So that's basically what's going to happen here. So if you want to see, I have some, there's everything that I just said is on the slides. Sorry if I talked a little bit fast. So I'll just kind of go through this a little bit real quick. Just more about shell code. It's basically just any code that runs in the shell, and you can get a lot of it from here, which this is just basically a huge repository of shellcode that does all sorts of things. Mine just ran a shell, but in reality, like there's lots of like reverse TCP and lots of different maybe like networking things you can do as well. Here's the thing about NOP slides. Okay, so with heap overflows, this is sort of the next thing I was going to want to talk to. It's basically, it's almost exactly the same thing, except instead of overflowing the stack, which is what we were doing here, we're overflowing the heap. And generally, they're a little bit more difficult to exploit because the heap is generally more random than the stack. But and this can help us get around things like non-executable stack segments, because I actually had to, when I compiled that vulnerable program, I had to disable certain checks that were in place to stop it from basically prevent me from running things on the stack. So things like heap overflows can sort of get around these protections in the real world. So an example of this was last year, there was actually a critical bug in the program sudo, and it went unnoticed for about 10 years. But with this bug, it was a very similar idea to what I just showed you, but with the heap. Basically, someone was able to trick some program to like make a string that they typed in unlimited, and from there, they were able to use privileged escalation to get full access to a system, just like I was talking about. And that was it's kind of like a wake up call to a lot of people, because something like sudo, like you'd think everybody who's ever used Linux has used sudo, so you'd think that it would be like 100% fully safe and robust, but even as recently as last year, there's still critical vulnerabilities like this that can like totally change everything. So, all right.
All right. So, as Rory was kind of getting into here, as we're like working on CTFs and stuff, it's really easy to kind of get lost in what we're doing, right? You're just running a shell on your own computer. You have a binary that you downloaded from some CTF website, just filling it with A's and NOP slides, trying to override the return address, write your own code in there. And at the end of it all, it just spits out a flag, right? Nothing dangerous, nothing very important is happening. But buffer overflows, like in the real world, are consistently like covering the top 25 vulnerabilities, right? So if you go to this list, none of them explicitly say buffer overflow, but there's lots of things in there like bad reads, bad writes, that would constitute a buffer overflow. And it's like always increasing somehow, even though they're generally regarded as pretty difficult to find, and even if you find them, pretty difficult to exploit, right? So I'll just go into some of the higher level details of what it really looks like to have a buffer overflow in the real world. Right, so the first thing, kind of background, I know most of you guys haven't taken CS111. This will come up when you do. Computers see all programs in terms of processes, right? So whenever you run a program, it creates a new process on the computer, usually by forking. And it's not that important to know all the details of processes, but basically your program is isolated to whatever process is running it, right? So different processes have different permissions, different things are going on, right? And so if you put a buffer overflow into a process and then it finishes, the process dies, it gets cleaned up by the OS, and your buffer overflow is gone forever, right? There's obviously ways to get around this because otherwise buffer overflows wouldn't be that dangerous. But this is something to keep in mind. So the first thing, which is something you'll go over at the end of CS33 and for most of CS111, is that processes have their own set of virtualized resources. Basically, every program running on your computer thinks it's the only thing there, and it thinks it's the only thing executing. This is why when Jerry didn't put the ×5 on the zeros, it still went to the right address in the code, because basically what the program is looking at is a full stack that it thinks is all of memory, right? So all of the code is going to be in these lower addresses that start with a bunch of zeros. On the other hand, if you are doing like code injections and it's like in the stack area of memory, that's going to be higher always, because again, the program thinks it has the whole of memory to itself. So those are going to be at the very high end of memory. And if you're doing code injection, which I think is the first part of the attack lab, make sure you don't put zeros at the front, make sure you don't like cut off the address early if somehow it doesn't show you the whole thing. But basically, anyways, the important part of virtual memory here is unless otherwise specified by the OS, programs can't see each other, right? So if you have a buffer overflow in some really low priority, like low permissions program, and it's not able to see anything else running on the computer, chances are you're not going to be able to do much with it. But once again, there are that little sort of at the end where I mentioned again that the exploit is bound to the process is like there's caveats, there's ways to get around this. And one of the things in the real world that makes use of a lot of these sort ofs is viruses, right? So if you look at buffer overflows, go to the history section on Wikipedia, all of the famous examples are worms, right? This is for a lot of obvious reasons, right? Like if you just have a buffer overflow that runs a shell and doesn't do anything else, nobody's really going to know about it, right? But once you get a shell running, it's pretty easy to add stuff on from there and sort of take over the computer, start connecting to other computers, and basically copy pasting your code everywhere you go. And so I'm going to use this as my own little excuse to go on a digression about viruses. This isn't something you totally have to know, but personally I find it really interesting. And I hope you do too, like when we start talking about how viruses work. Okay, so as you know, like from basic bio, a virus is something that hijacks like the nucleus of the cell, uses the cell's resources to make copies of parts of itself, put those together, and basically like keep building it until the cell explodes, and then it keeps going to other cells, right? So at a high level, this is how computer viruses work. But at a lower level, you kind of have to realize what we're building here in a virus is something that's going to print its own source code to other places in the computer, right? So I want you guys just to take like maybe 30 seconds to think about this, right? If I told you your next project for CS33 was to write a C program that doesn't take in any input, but as output prints its own source code, what would you write? Do you have any ideas? Anybody? Or if you're kind of struggling, what are the things that seem to make this hard to do? Yeah, Jerry.
What about a print statement?
Okay, yeah. I mean, I have that there. Let's consider a print statement, right? So if you say like printf and you have the open parentheses, what do you put first in that print statement to make this code print itself? Yeah, Benson.
Maybe another printf.
Sure, you could have another printf. And then you might need another printf, right? And now you've got 3 in the code, but you've only got 2 in the print statement. So you need to add another one there. And you can kind of see very quickly, this is just going to keep going. And you're going to have like one of those trippy animations where it's just like a repeating GIF where you're going down a tunnel, right? So we kind of need to change the way we're looking at this. And sorry, I won't stay on this for too long, but we're just going to think about this sentence right here, right? So think about this as an instruction to your computer. Or imagine you wrote this on a paper and you give it to your little brother or something, and you tell him, follow this instruction, right? So he's going to read it and he's going to say, write down 2 copies of the following, the second in quotes, right? And so he's going to see what's in quotes, and if he's a reasonable person, he'll write down the thing in the quotes, and then we'll write down another copy of it, and we'll put that second copy in quotes. And lo and behold, you've created an instruction that when someone reads and executes it, it duplicates itself, right? So let's kind of take a second to think about why that worked, right? So the print statement issue was that it couldn't print itself, right? No matter what you put in there, you're never going to be able to capture that outside part, right? But you could very easily, if I gave you a function and said, make a function that prints this source code, you just plop that right in the print statement, right? And you have no problems whatsoever. So you can kind of think about what we want to do as sort of two parts that mutually print each other, right? Obviously, if you just tried to do that straight away, you would run into the same problem. It's like mutual infinite recursion, right? Instead of one tunnel that goes into itself, you have two tunnels that just go back and forth. But this is the basic idea, right? We want some way to have some part of it not be self-referential. And the basic idea of what we're about to do is that part A is going to print part B, and part B is going to print part A. And there's a little bit of a tricky way that we make this happen. So what we're going to do is we're going to have part A go ahead and print B's code, right? And B is not going to be aware of A or anything that's going on. It's not even going to be aware of itself. But it's just going to take whatever is given to it as input, and it's going to print out a print statement that includes its input, and then the input after it, right? So think about what happens if we run A, and then feed A's output into B, right? Then what's B going to print out? B is going to print out a statement that says print my code, right? And that print statement that says print my code is A's code, right? And then it's going to just print its code because that's what it was given as input. And so what you end up with is you have A's code, and then following it immediately is B's code. And so if you put these together into a function, what it would print out is exactly its code. And so this is the basic blueprint for how a virus works. And so the last step, obviously the virus we just ended up with doesn't do anything but print itself, right? Which would make it like the most useless virus of all time. I guess not totally useless for reasons I'll get into in a second, but if you want to do more things like, say, connect to another computer, open a shell, write Sammy's my hero into their computer's memory, you have to add a part C which executes some arbitrary behavior. And this is probably the easiest thing we've done. You're just going to make the modification there under a resulting program, right? Basically, every time you see B's code, just add C to the end of it, and it'll work just fine. This is something that comes up in 181. I don't know if it comes up in all the sections, definitely with Sahai. But it's called the recursion theorem. It's like the theoretical foundation for you being able to actually use recursion, which is probably something you take for granted. But yeah, just something to think about, that like one of the earliest things that was discovered in computer science is now like the theoretical basis for viruses. I don't know. I just think it's pretty cool. Anyways, so story time. Basically, the Morris worm is the very first famous buffer overflow example and the very first virus that was on any sort of network and was well known and well documented. So the idea of the Morris worm, it was created by a grad student at Penn State. He let it loose on a large academic network that actually spanned a bunch of the Ivy Leagues, actually had some connections in Europe as well. They managed to get it disconnected before it made it all the way there. But there were like 60,000 computers connected to this network, and the Morris worm managed to infect and basically destroy 6,000 of them. So pretty tragic for a grad student's little social experiment or pen testing experiment, I guess I should say. He was just kind of bored and wanted to test out like a bunch of things he thought were wrong with the way networks worked at the time. And he had found this buffer overflow in an old terminal daemon. Basically a daemon, if you're not familiar with the term, is a program that runs on a port, right? So web servers have HTTP daemons, and that's how they like keep taking requests. And all the computers on this network had a daemon that ran this program called fingerd, right? And basically, fingerd was just like something you could use to check in on your friends. It's just like pinging them. It's like, are they in? What's their computer doing right now? Would this be a good time to talk to them? In many ways, it's like not super helpful and not exactly a great idea to have. But the main problem with it was back in the day, people didn't download binaries like we do today, right? They would just download the source code, compile it themselves with whatever options they wanted, define their own constants, and then run it as they wanted. So fingerd, when let's say I connect to Rory's computer and he's got his fingerd running on his port and I want to see what's Rory up to, right? And so I go ahead and I type in some information that I want, and fingerd is going to give me some response back, right? And Rory has decided when he compiled his source code, hey, this isn't, whatever Steven wants from me is not going to take more than like 200, 300 bytes, so I'm going to set that to be my buffer size. But Morris knew that everyone set their buffer to be like 265 bytes, I think was the number. And so he wrote his worm basically to overwrite that buffer and do what Rory and Jerry have been showing you all this time. And basically what it did was, just like how Rory opened a shell, it just opens a command interpreter, right? And this is part of the thing that I was going to get into earlier. When you're injecting code and you have ROPs and knob slides and code injections and things like that, this goes back to virtual memory as well. You only have so much room to inject code, right? So really what you want to do is open up a different process, and that's where all the power of buffer overflow comes from, but that's also what makes it hard. But what he was able to do was he was able to open a command interpreter that basically ran the code that was sitting in the worm, which, as we just explained, copies the worm into the computer and had some extra steps to like disguise itself, fork the process, which made sure that if anything happened to fingerd, you now have a separate process running your worm, and it's not going to shut down so easily, and it would just repeat and take over the network. I guess one oversight that not an oversight on my part, but an oversight on Morris's part that I didn't put on here is that, so when he was thinking about making this worm, he goes, okay, I don't want to destroy computers, right? So what I could do is I could check, does this computer have my worm already? And then if I see that it has it, then I'm not going to infect that computer, right? Because if you keep adding the worm, the computers are going to have to keep running multiple copies of the worm, and you're going to eventually like run out of memory and storage for the worm. It's basically going to fry the computer, right? But the problem he saw with that was, well, people are going to start seeing my worm there, and they're just going to tell my worm, oh yeah, the worm is already here, please don't come in, right? And he's like, that's too easy of a solution to this. So no matter what, I'm going to infect computers 14% of the time. But as you could probably guess, that didn't work so well because you get loops back and forth between computers. And basically, a lot of the 6,000 computers full of academic material and like research just got completely nuked by his worm. And this was also, it's also part of what made it like, I think the first time someone had to pay a fine or like was officially charged for creating malware. So yeah, so definitely don't do that. But yeah, for your own curiosity and edification, that's some stuff about buffer overflows and viruses. So that's it for our workshop. Please stay connected with us on Instagram. If you have any questions, feel free to ask us in our Discord or the ACM Discord, which is linked on the ACM website. And then on our website, we have some challenges up for you to try. We do have some from the past weeks as well. Please solve those. They're a lot of fun. The officers would definitely like you to solve them. Maybe if not now, then at least during CTF after dark. But yeah, let us know if you have any questions about any of the material today. And thank you for coming.